Imagine a small drone navigating through thick fog where cameras fail and LiDAR is too heavy to carry. What if a single radar measurement could instantly reveal the dense 3D structure around it? The researchers behind RadarSFD have cracked this challenge by teaching radar to see like LiDAR using just one frame. Let me first show you exactly what problem they set out to solve. Building on this motivation, the core challenge is that size and weight constrained robots need dense 3D perception in harsh conditions. Traditional radar gives you sparse, incomplete scene understanding from a single measurement. The key insight here is that while existing approaches stack dozens of radar frames to build up resolution, RadarSFD aims to extract maximum information from just one measurement. This eliminates the need for complex motion patterns or temporal processing. So how do they achieve this seemingly impossible task? The breakthrough insight is elegant. Instead of teaching radar to understand 3D geometry from scratch, they transfer existing geometric knowledge from pretrained vision models. The diffusion process then fills in missing details while staying anchored to the actual radar measurements. This diagram reveals the elegant architecture at work. The frozen VAE encoder creates a shared latent space for both radar and LiDAR data, while the pretrained UNet brings in geometric understanding from monocular depth estimation. The conditioning mechanism concatenates radar information directly with the noisy latent to maintain spatial alignment throughout the diffusion process. Let me walk you through the technical mechanics that make this possible. The architecture cleverly combines several key components. The frozen VAE ensures consistent encoding between radar input and LiDAR targets, while the Marigold pretrained backbone brings rich geometric priors. The dual space training objective is crucial. It prevents the model from generating plausible but incorrect scenes by tethering outputs to the specific radar measurements. The training process teaches the model to reverse the noising process while staying conditioned on radar measurements. During inference, this learned denoising ability transforms random noise into structured dense point clouds, guided by the single radar frame input. These implementation choices prove critical for success. The light thresholding retains weak radar signals that contain structural information, while the pixel space losses prevent the diffusion model from generating realistic but incorrect scenes that don't match the actual radar input. Now let's see how well this approach actually performs. The results are striking. RadarSFD achieves better point cloud accuracy with a single frame than Radar HD achieves with 41 frames. This represents a fundamental breakthrough in single-frame radar perception, while also delivering significant speed improvements over competing diffusion approaches. These visual results demonstrate the dramatic difference in reconstruction quality. While classical CFAR processing produces sparse, disconnected points, RadarSFD recovers detailed wall structures and narrow passages that would be critical for robot navigation. The dense point clouds rival what you would expect from LiDAR sensors. While the approach shows remarkable capabilities in recovering fine geometric details, the authors honestly acknowledge current limitations. The occasional hallucinated points and missing geometry suggest that larger, more diverse training datasets could further improve performance. The ablation studies reveal crucial design decisions that make this approach work. These ablations provide a clear recipe for success. The geometric priors from Marigold prove more valuable than semantic priors from general image models, while the pixel space losses are absolutely critical for preventing the model from generating plausible but incorrect reconstructions. This comprehensive ablation table clearly shows the impact of each design choice. Notice how removing pre-training or using latent-only losses causes dramatic performance drops, while the full method with Marigold initialization and dual space training achieves the best results across all metrics. Let me wrap up by highlighting why this work matters for the broader robotics community. This work opens new possibilities for robot perception in challenging environments. The ability to get LiDAR-quality point clouds from a single radar measurement could transform applications from search and rescue drones to industrial inspection robots that need to operate where traditional sensors fail. From a research perspective, this work establishes a new paradigm for radar-based perception and provides a clear methodology for transferring vision priors to other sensing modalities. The thorough ablation studies create a reproducible foundation for future research in this direction. RadarSFD demonstrates that single radar measurements can yield dense, LiDAR quality perception by cleverly borrowing geometric understanding from vision models and anchoring it to real sensor data. This breakthrough could fundamentally change how we design perception systems for robots operating in the harshest environments. To dive deeper into this fascinating intersection of radar sensing and diffusion models, visit emergentmind.com to explore the full research.